Okay, let's look at this entire set of ordered pairs under that relation. Then we denote that one like this. Okay, so the set is given and the relation among the elements of X is given. Okay? Then that is actually collection of those subsets, right? Which are equivalence classes. So there are many different ways we can do that, like S sub general case is m comma n, the order pairs, and we already checked. We can just choose any representative of each set, so it can be any number. That's a natural number. Okay. But another way and simpler one was, okay, instead of S, why we need a new letter? It's just saying it's ordered collection of ordered pairs, right? But it's an equivalence relation, so following the equivalence relation rule, then this is kind of small subclass. Okay? So we can use that notation, but what is our goal here? We want to develop the integers, right? So what happens for arbitrary integer, and we are going to use z, right? So eventually we are going to say this is same as that. Okay. So integer set is a collection, is exactly same as this set. So if you choose k from there, which means what? K must be one of these equivalence class. So question is, how can you define, right? When we can say k equals that, oh sorry, it's ordered pair, right? The same as that set. Okay? And the definition is here. Okay? That this k is the notation for that equivalence class, and that equivalence class is a collection of those ordered pairs, right? And this m n's are natural numbers, and m plus k becomes n. So that k came from this kind of difference between m and n in ordered way, right? So now you can see, let's say 1, 3, right? Then in that Cartesian coordinate system, okay, this set denotes this one, right? This is 1, 1, 1, 2, 1, 3, right? So this set denotes this entire subset, right? That is 1, 3. And once again, 1, 3 can be written by some other representative, which is 2, 4, right? So it can be written by 2, 4. And it can be written by 3, 5. So it can be written by, if you choose 101 for first element, then the second element must be 103, right? It's kind of same as 1, 3, right? So the difference is what? Is 2, right? We need adding 2 more to get the y coordinates, right? So that's the common properties of the elements in that subset, in that class, right? So this one, okay, can be written by 2, okay, because that set is same as collection of, okay, it's a collection of mn, right? Anything, any ordered pairs, and n's are natural numbers, and m plus 2 becomes n. Okay, that's the definition of this one, and this is much easier symbol for that, right? And because of this, what would happen if we change the order? The ordered pair means order is very important, right? So according to our definition, 3, 1 represent this type of ordered pairs, okay, such that m plus something equals n, right? And one of them is 3, right? And 1. So how much we need? negative 2, right? So good notation for that is going to be negative 2. You follow me? So the concepts are within that definition. So these are just the notation like a k or negative k, right? So we just need that much to handle certain things like that, right? So when you use this notation, we don't worry about, right, whether it's a positive or negative, right? We haven't developed that concept yet, but right, we just put down natural numbers naturally, then it can take care of positive, negative integers naturally, right? And once again, the most interesting one, useful one is that kind of collection, right? It's a collection of m and n's. Okay, let me. It's okay. Just okay, it's kind of off. So one of the most important, interesting one is like a 1,1 or 2,2, whatever you choose, right? Then it's actually a collection of mn, and mn's are natural numbers, but m plus something equals n, and at this moment, because it's 1 and 1, so we don't need to add anything, right? So we can denote that one for 0. So notation for that should be 0. Okay, so if we use this one, the good thing about this concept is this addition and subtraction and the multiplication can be handled. And this set is natural, the integer set z, which is x with relation, is closed under those three operations. And this is the rule of addition, multiplication, and subtraction. So it's very important here when we add these two, just add x coordinates and y coordinates as it is. And the subtraction, be careful, notation is subtraction, but as the coordinates values, we're still adding them. So t, but m with t, right? The outside ones placed for x coordinates, and inside coordinates becomes y coordinates of the result of subtraction. And multiplication, sorry, but it's kind of mt plus ns, okay, for x coordinates, and nt ms, right, for y coordinates. Then when you look at the actual result, this one is well kind of presenting our usual addition, subtraction, and multiplication. So in other ways, we can think like this. Whenever we have that ordered pairs, and that representing this difference between n and m in that order, n minus m, right? So it's a typo. So if we have this ordered pairs for s comma t, then that representing t minus s. That will be a notation for that k we have before. So all the collection of those ordered pairs m comma n plus m, this one is the kind of simplest way, right? 1 comma n plus 1, and that is for number n, right? And if it's a negative n, then it's going to be n plus 1 minus 1. Okay. So because of that, 1 comma 1 or m comma m should be written by s, denoted by s. Okay, then let's just check how effective this new method for calculation. Let's say y 3 plus 5 equals 8. Now we have two different ways of look at those numbers. 5, 3 are the sets, right? And using the previous chapter's notation, it's going to be really complicated, right? But if we use this new way of think, then 3 can be written by, now it's a positive number, then it's always 1 comma something, right? And how far? It's that much difference, so this will be most natural way to give the representation of number 3, right? And 5 is the same way, so 1 comma 6, right? But if you want, you can choose just any number, right? It's still okay. So it's going to be, if you want to start with 7, then all you need is just 10 is enough. Okay? For 5, just use any number like 1 or 7. The next one is 112, right? But as you can see here, instead of that, this should be much simpler, right? So that's the most natural way to give the representation of it. So we already know what is going to be the notation for integer 8, right? It's going to be 1 comma 9, right? But let's just try to find 3 plus 5. Then that is 1 comma 4 plus 1 comma 6. Then according to that definition of addition, it's same as 1 plus 1, right? X coordinates together, and 4 plus 6. So together, then that becomes 2 comma 10, right? But what is the meaning of 2 comma 10? 2 comma 10 is 2 comma 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So it's going to be here. So that belongs to this group, right? Collecting this one. So what is that? It's 1 comma 9 because it's 2 comma 10, right? So this is one of the representative of this set, right? And we found out that is 8, right? So technically you don't need to state this one, right? This one itself can be written by the integer 8, right? So that's the kind of explanation or proof. Next one, let's confirm the subtraction, right? That's the kind of one of the main reasons we want to develop this new style. So once again, 3 can be written by 1 and 4, right? And 5 is written by 1, 6. And negative 2 is, now if you want to start with 1, then the difference must be like that. So we have to put negative, right? But this is not good because when in this notation, all these ordered pairs, the coordinates of the pairs must be natural numbers, right? So we cannot accept negative number there. So that's why we have the other way. If it's a negative number, then we want to put 1 for y coordinates, right? So how much do we need? It's a backward, right? So 3 comma 1, then the difference will be negative 2, right? So 3 minus 2 equals 1, right? That's the way we define. Okay. Then from there, what is 3 minus 5? Then according to our previous definition, we're still adding them, right? Be careful, it's not subtracting. Okay, it's a common mistake. It's m plus t and n plus s, right? So it's just kind of the other way of addition. Okay. So 1 comma 4 minus 1 comma 6 is 1 plus, everything is plus, but not by the coordinates, right? It's 1 plus 6 and 4 plus 1. Then it becomes 7, 5. And we know the difference is negative 2 in that direction. So we know it should be negative 2. But if you really want to get that simplest format representation of it, then look at here, which one is the smaller one? 5, right? Then change that one to 1. Then how much we subtract 4? I subtract 4 from there, then it's going to be 3, right? And that is what we have over here. So it's more clear. We can claim that is negative 2, right? So it doesn't matter, but maybe this is better explanation for your students. Okay, so through these two examples, we actually find out that we didn't develop new rule about negative integers, right? Negative integers is kind of notation, that's all. And it can be explained and constructed by just through the arithmetic, the operations, right? So that's the kind of one of the good reasons why we want to develop our number system in this way. So if we have this, just imagine, and you kind of explain this one to your students, then they never ask, they might ask, what is the meaning of negative 2? In our traditional method, we have to explain, oh, I borrowed 2 apples from you, or that kind of concept, right? But in here, negative 2 is what? Just the name of one of that set, right? Like all these sets have, right? So this is 0, and this kind of 1, 2, 3, and these are negative 1, negative 2, negative, right? You can see that, right? So this is just name of that set. That's it. So it's more abstract way of a definition of numbers, right? But we can use this one to explaining our daily kind of life situation. Okay, if it's an algebra, this is very important. So you are going to see this one in abstract algebra course later. But let's just try to find out that 0 should be the additive identity, which means if you're just adding 0 to any integers, or actually any real number later, but it just returns that integer, okay, again. It doesn't change at all. And of course, this case must be also symmetric, right? So 0 plus n must be also same, but it's not algebra course, so let's just check this one only here. And now n can be written by anything, right? But most likely it's better to have 1 and 1 plus n or n plus 1, it doesn't matter, okay? But if you want to use the previous chapter method, n plus 1 is more natural. So let me just use this way. And 0 is 1, 1 is the best way to denote. Then what is n plus 0? It's 1, n plus 1 plus 1, 1. So by the definition of addition, we have coordinate-wise addition, right? So 1 plus 1 and n plus 1 plus 1, right? So it becomes 2, n plus 2. So we can say directly the difference, how far we have to go, we need to add plus n, right? So it's going to be n. Or you can kind of reducing the number to 1. So how much we need to change? Subtract 1. So subtract 1 from there, we got n plus 1. But that is exactly this one, right? So it doesn't matter which way you go. Okay? But this one shows why n plus 0 is n. And you can do the same way, right? So please do this one for your homework, but no. So lastly, how about multiplication? We didn't cover anything about multiplication, but just to apply that rule, then you will get that concept. And in the homework, you have those, right? Okay. I mean, not this one, but you need those multiplications here. So please practice with that. In here, I only want to show that 1 is the multiplicative identity, which means 1 times n equals n, or n times 1 equals n, right? Same thing. So let's just do this. 1 is 1, 2, and n is 1 comma n plus 1, right? So 1 times n is 1 comma 2 times 1 comma n plus 1. Then what was the rule for product? We just multiply m and t plus middle ones, right? Outside one, middle ones, and adding them to make the x coordinates. And the next one is coordinate-wise multiplication and adding them for y coordinates, right? So in here, for the x coordinates is outside one, right? So 1 times n plus 1 plus inside, so 2 times 1 for x coordinates, and for y coordinates is coordinate wise, so 1 times 1 plus 2 times n plus 1. So when we simplify it, it's n plus 1 plus 2 and 1 plus 2n plus 2, which is n plus 3 and 2n plus 3, right? Okay, so in this case, you can think how much we need to change like this. We just need to add n, right? But maybe it's better how much we have to subtract to get 1, right? Then it's n plus 2. Be careful, right? We have to subtract n plus 2. So we subtract n plus 2 from there. We have 1 n left and plus 1, right? And that is n by that. So for your homework, please do n times 1 because the way of multiplication is different, right? So you have to calculate this multiplication according to that formula and show the result is also n, right? That's actually, we have to do it, but okay. Okay, then the homeworks, I think it's again. Now, when you try to do this one this time for any integer even, so it's including natural numbers, this one is way easier proof than the ones in the previous chapter, right? You have a hard time to do it, right? There's a reason for that because you see how easy to doing this way, right? When we apply this new rule here, okay? And the others is a simple calculation, but please check, okay?